Hi, my name is Brad Rieger, and I'm the Principal Architect at Engraces Technology. Today, I'm going to talk about a modular architecture we're developing for our next generation of data center products. For the last 20 years, the server world has been dominated by x86 CPUs with Linux and Windows, dutifully marching to Moore's Law and the performance gains it provided almost for free to the server designers. While server designers kept busy during this period, much of it was simply turning the crank to incorporate each new x86 CPU. To make a long story short, the gains that system designers and customers have taken for granted for 4 decades are flattening out. They're still improving, but not nearly as fast as people would like. Today's problems require a hardware-software co-design approach that encourages innovative hardware to go with the new software to drive performance dramatically higher. Anyone working on HPC, machine learning, or deep learning is well aware of this. Anyone aware of crypto mining is also well aware of this. Witness the GPUs, FPGAs with custom hardware algorithms, purpose-built ASICs, and a variety of domain-specific hardware and software. With all the hardware variety now and in the near future, how should system designers exploit this opportunity? Well, we could staff up multiple teams to develop different products optimized for each workload using the best hardware available. But that's an inefficient use of people, equipment, energy, and natural resources. We think a better approach is to use modularity to break down complex systems into simpler, reusable parts that can be mixed and matched to create new systems. This isn't a new or unique concept, but we think now is a good time to embrace it. Based on a recent OCP Tech Talk on the DC-MHS, or Modular Hardware System, a group of influential companies agree with this as well. I encourage you to watch the OCP Tech Talk and review the documents. We agree with all the tenets and have come to many of the same conclusions. Legacy server motherboards contain CPUs, memory, some I/O devices, and a whole mess of manageability logic that's often tuned to each OEM's requirements. The first step in our divide and conquer approach is to attack the most complicated board in a server and break it down. As OCP has done, we want to move the BMC and most of the messy management logic onto a smaller separate board. We like the DC-SCM that the OCP has defined. As most motherboards have always done, we want to implement high-speed I/O functions like NICs, DPUs, and storage HBAs onto separate plug-in cards. We'll move HDDs and SSDs to separate subassemblies and even to separate chassis. We could move the main memory, but that's not efficient right now. We can augment main memory capacity and throughput by using CXL memory modules that are in development today. What's left after stripping off all the above is the CPU memory complex, related power regulation, and high-speed PCI links that we'll use to connect to other modules. This is the most complex assembly in our modular architecture, but we've minimized the size and the features as much as possible. To develop this new modular architecture, first, we define and develop as many chassis as we think we need for end products. We define and develop the functional modules needed and the interfaces between each of those modules. We develop one or more HPMs to be the server's engine. Then we can mix and match modules in the different chassis to create products our customers want to use. There's a lot of work to develop the first set of systems using this approach, but the payoff comes when making any further changes. If we want a CPU platform from another supplier, we create a new HPM and it slips into place where the other HPM worked. No changes are required to the chassis or other modules, in particular to all of the messy management logic. If we want a new I/O or storage function, we can develop a new functional module and it fits into place in one or more chassis with no changes to the HPM. When we want to refresh the HPM to the next generation CPU, we develop a new HPM, again with no other changes required. Obviously, we can make changes to multiple modules at once, but the point is, we don't have to. Here's a simple example that shows an HPM with a given CPU family going into 4 different chassis with different I/O and drive configs. The second row shows the same thing, but now with a different HPM using a different CPU family. Obviously, we can add more rows, more HPMs, to increase the matrix. Here are some examples showing I/O and drive configs we could support in a 1U server. One has a set of E1.S drives, another has a set of 2.5-inch drives, and the next two show how the modularity can allow mixed configurations of drives and, for example, CXL memory modules. Here are some similar examples using an ORV3 chassis, where drives and I/O are all on the same side. We also believe in modularity at the rack level. We can disaggregate storage from the servers, create JBODs of HDDs or SSDs, and access those drives over SAS or NVMe over fabrics from the servers or through top-of-rack switches. Orchestration software can compose virtual servers by allocating NVMe namespaces to VMs or containers on the compute servers, or to DPUs or to dedicated storage servers. We can disaggregate GPU server clusters from the head nodes used to feed them to allow customer-specified head nodes and to change the ratio of CPU and memory to the GPUs. With PCI fabrics and orchestration software, we can dynamically compose virtual servers from pools of shared GPUs and storage. We're big believers in modular systems and composable disaggregated systems. In addition to our modular servers and storage, we have another tech talk on rack infrastructure with advanced cooling solutions. I encourage you to review that tech talk as well. Thank you.